is Module 11, Lecture Notes 22. Today we're going to start our lecture by introducing a new formula to you. This one is called molality. Okay? It is the number of moles, think molality, moles, of solute per kilogram of solvent. Okay, and here's your formula. You do need to know it. Molality will be the unit's little m. Okay, and so over here to the side, these past 2 weeks we've talked about two concepts that are very similar, molarity and molality. Okay, and I just want to make sure you know that they are calculated differently and they do have a different letter attached to them. Molarity, when we talk about concentration, is going to be a big M. Molality is going to be a little m. Okay? Today we're just going to be talking about molality, so we won't be going back and forth. We're just going to learn this new one today. The way we calculate it using this formula is we're going to take the moles. Okay, so here they've given us 3.4 moles of salt dissolved in 4.5 kilograms of water. And so it's pretty simple. They are going to have us do moles on top divided by kilograms on the bottom. And you'll just plug that into your calculator. 3.4 divided by 4.5. Remember, since I'm only putting 2 sig figs in, I really only need to keep 2 sig figs in my answer. And you'll label it with a little m, and you're finished. Okay, seems too simple to be true, right? Well, not all of your problems will be given to you in moles and kilograms, but we have learned enough in this course to be able to get to moles and to get to kilograms. So let's take a look at this next problem. A solution is made by adding 45 grams of zinc chloride to 150 grams of water. Okay, so for this first part, you need to take grams and get moles. Okay, and for the 150 grams of water for your solvent, you're going to need to use your metric conversions to get that to kilograms. I would like you to pause this video and test yourself and see if you can get to moles and kilograms to solve for molality. All right, so the first thing I needed to do was add up the molar mass of zinc chloride. So I took the molar mass of zinc plus 2 chlorines, added them together, and I got about 136. So you take grams over 1, you're going to divide by 136 to get your grams to cancel, and remember that will switch it into moles. So I have 0.33 moles for my top number. And I need to get this 150 grams of solvent into kilograms. And so the conversion from grams to kilograms is to jump to the left 3 spaces, or it's the same thing as dividing by 1,000. And so on the bottom of my equation, I will have 0.150 kilograms. Okay, so you'll divide those in your calculator, and you should get 2.2, and you'll label it with the little m for molality. Okay, so that should help you see 2 different ways to get to your molality answer depending on what you're given. Now, why does molality matter? Okay, the reason you need to know how to calculate molality is because it's used in 2 concepts: freezing point depression and boiling point elevation. Okay, so go ahead and scroll to the bottom of your page and we will start talking about freezing point depression. Okay, the concept of freezing point depression says that when a solute, okay, so think of like a solid being dissolved in a solvent, the freezing point of the solution actually changes. It will be lower than that of the pure solvent. Okay, so what this is saying is when you dissolve something in something else, it changes the temperature at which it freezes. And I happen to think this is really cool. I know, you have to love science and be kind of nerdy to get into this stuff, but this actually applies to something you're going to see this winter, okay? Why do we spread salt on the roads in the winter? Freezing point depression, okay? When you dissolve that salt with the slush that is already on the roads, it keeps the water from refreezing. It lowers the temperature at which it will freeze again. For those of you that like visual pictures, I do too, let's look at what's happening on an atomic level. So let's say that these are little molecules of just plain water in this box, okay? When they freeze, remember we are lowering their energy. They're going to start to slow down their movement and go from the liquid phase to the solid phase, okay? So maybe draw that they're starting to slow down. And over here to the right, I'm going to write, they're going to slow down and they're going to lose energy to become a solid. Okay, so that's what these guys are doing. Now in this picture over here to the right, I not only have water, but I also have some other particles dissolved with the water. And we're going to say that that's salt. So this picture is salt and water. Okay, so now when these water particles want to slow down and lose energy, there's somebody in the way, and that's the salt particles. It is not as easy for the water molecules to form a solid because they're bumping into the salt. Okay, so you might write in the way, harder to slow down and freeze. So that kind of gives you a visual representation of what would be happening in two different cases. The solute particles actually get in the way and they prohibit freezing at a normal temperature, and so you have to go to a lower temperature to get this solution to freeze. Okay, so this is the equation for freezing point depression. And we're going to go through and define what each of these variables are before we do a practice problem. Delta T is the change in temperature. Okay, that's going to be how much the temperature lowers, or the change in temperature when we have a solute dissolved in a solvent, the change in temperature for its freezing point. Okay, the negative I is the number of ions, and we will come back to this one. Kf is called your freezing point constant. And since it's a constant, it will be a number that is given to you in the problem. You'll just have to plug it in. And then M, well, we just learned that up here, that is your molality. And we learned how to calculate molality because you need it in this equation. Okay, so let's come back to this negative I. Negative I stands for the number of ions that your solute can break into when it's dissolved in a solution. So I have some different solutes down here, and we're going to practice telling how many different ions or how many pieces it will split into in a solution. So let me do the first one with you. If I put sodium chloride into water, okay, it will break into a sodium ion and a chlorine ion. Okay, remember sodium's positive, chlorine's negative. It will split apart and those sodiums and chlorines will be moving around. This is two ions, a sodium and a chlorine. So you're just counting basically how many pieces it splits into. Okay, what about CaI2? Okay, you're going to split into a calcium that likes to be a 2+. And then you have I2, which means you have 2 iodines, and each of them like to be a -1. So if you were to count up how many pieces or how many ions that is, I would say 1, 2, 3. 3 ions. Okay. What about something with a polyatomic? For polyatomics, it will still split apart because this is aluminum and nitrate, but you're going to keep this nitrate together as a whole unit. Okay, so you'll have aluminum. What's its charge? Aluminum likes to be a +3. And then you have 3 of this nitrate group. So I would just write it like this: nitrate, nitrate, nitrate. Okay, and each of those are a -1. So if we were to count up the total number of parts that this breaks into, we have 1, 2, 3, 4. This is 4 ions. Okay, you might write yourself a note here: polyatomic stays together as a unit. Okay. Now let's take a look at the next two. What is different about these? This compound and this one, they are actually covalent. They are made up of non-metals only. Okay, they don't have a positive ion joining with a negative ion. They are non-metals only. And because of that, they don't dissolve in water very easily. They will not break apart into ions. So these are one piece, they stay together. Okay, you might write yourself a note: these are not ionic, they're covalent. Okay, and so you can just count that as one molecule or one piece. All right, I want you to do the last one, Mg3N2. Decide, is it going to break apart? Will it stay as one piece? If it does break apart, how many would you put here for its number of ions? All right, this is ionic. It will break apart. I have 3 magnesiums and 2 nitrogens. 1, 2, 3, 4, 5. This will break into 5 ions. All right, so now that we know what freezing point depression is and the formula for it and what all the variables mean, let's flip over to the other side and do one together. Okay, so here at the top, I've just copied the equation from the other side. We have change in temperature equal to -I, which is our ions, times Kf, which they've given to us, times molality. Your first step off to the side here, you will need to calculate molality. Okay, let me circle the things that have been given to us. We're going to be taking 15 grams of sodium chloride and adding it to 100 grams of water. I want you to use these two numbers and practice what we learned in the first part of this lecture to calculate molality. Do that here off to the side, please. Okay, so to get molality, I first needed to take my 15 grams of sodium chloride, I divided by the molar mass to get moles. Okay, moles divided by kilograms gives me 2.6 for molality. Okay, now we have everything we need to do our freezing point depression equation. So I'm going to say change in temperature is equal to negative. How many ions will my sodium chloride break into? It's going to break apart into a sodium and a chlorine. That's 2 pieces. So I'm going to say -2 times Kf, which was given to us, 1.86, times molality, 2.6. in our calculator, if we do that, make sure you're using your negative button, not the minus button. -2 times 1.86 times 2.6. We should get -9.7. And since this is a temperature, it's going to be in degrees Celsius. So what that is telling you is that the change in temperature is 9.7 degrees colder because the salt is dissolved in it. It's going to freeze at -9.7 as opposed to 0 degrees Celsius. It lowered the freezing point of that water. Okay, and you can even make a note of that. Lower than 0 degrees Celsius. Okay, so that's how you would do one of those problems. Okay, boiling point elevation is virtually the same thing, except we're talking about the temperature at which the solution boils instead of freezes. This would say that when a solute is dissolved in a solvent, the boiling point is actually higher than when it's just a regular solvent. Okay, so let's look at an example of this. Here's just pure water. And when something boils, it needs to gain energy to escape to the gas phase. So these particles are starting to move faster and faster. They need to gain energy to go to the gas phase. Okay. Well, what happens if we add some salt to the water? I am sure you've heard of this before. If you've ever been making pasta and somebody says, hey, add some salt to the water. Why? Do you know why? It's because of boiling point elevation. So let's look at this. Now I have pieces of salt dissolved in the water. And so as these water molecules are trying to escape to the gas phase, they bump into the solute. Okay, so you can write that off to the side. So it will actually take more energy at a higher temperature to get the water to boil. So pasta water that has salt in it is actually hotter than regular water. Okay, kind of cool to think about that when you add salt to your pasta water to cook, you've actually raised the boiling point. So it should theoretically cook a little faster. So that's chemistry in your kitchen for you. Try it next time. All right, so let's look at our equation. All of our variables are the same. We have change in temperature, we have I. Here's the boiling constant, Kb, and then molality. The only thing I would note is that there's no negative sign. Okay, because we're talking about a temperature that has been raised instead of lowered. Okay, so this is a positive I. And this is your boiling point elevation equation. Okay, so in this problem down here, I'm not going to walk you through it step by step because it's virtually the same as the one that we did up here. I would like you to try it, and then I will put my answer up here so that you can see how I worked this one out. Okay, so here's what I did first. I took my grams of NaCl divided by the molar mass to get moles, because I need moles over kilograms to get molality, little m. Now I'm ready to plug into my boiling point elevation equation. The change in temperature is equal to I, which is the number of ions that your solute breaks into, 2 ions, times your boiling point constant, given to you in the problem, times your molality, which we figured out right here. So if we put all that in, we'd have 2 times 0.512 times 0.23. And I get 0.24. And what is that? It's a temperature, so it should be in degrees Celsius. Okay, let's read this question really carefully. Okay, so in cooking pasta, the chef adds 20 grams of sodium chloride to 1.45 kilograms of water, brings it to a boil. What is the temperature of the boiling solution? Is it this? This is just the change in temperature. This is how much the temperature went up as a result of the salt. So what is the temperature of the new solution that is boiling? Okay, you need to know that water boils at 100 degrees Celsius. Because he's added salt to it, we have a change in temperature that has gone up by 0.24 degrees Celsius. So to actually answer this question, you would need to say that it is boiling at 100.24 degrees Celsius. Okay, so just make sure you're fully answering the question. Do they want the change in temperature or do they want the new temperature? Okay, hope that helps you work through these, and as you go through life and you're thinking about why do we do certain things that we do or we've always done, bring it back to some chemistry concept that we've learned. Cooking, salt on the roads. Hopefully you will see some of those things and you will be able to explain them to friends and family. Have a good week.